Hey guys, welcome to chapter 15. In chapter 15, we're going to talk about chemical equilibriums. So what I'm going to do in this video is I'm just going to introduce this idea of an equilibrium. And to do that, I'm going to use a real life example. So I'm going to use hemoglobin and oxygen, how it binds and releases it. And it'll give you just a really good picture of what an equilibrium looks like. So here we see a molecule of hemoglobin. Molecule of hemoglobin, this is something that we find in our blood. It's a protein that reacts or attaches to oxygen. So there's four spaces where oxygen, let me get my pointer so you can actually see where I'm pointing. There's four spaces where oxygen can bind to this hemoglobin, okay? The very generic reaction for this, HB stands for the hemoglobin molecule. O2 is the oxygen that it'll bind to or release. And when they are bound together, when they're in a complex, that's where we see this hemoglobin oxygen complex. So this is bound together, it's holding on to a hemoglobin. This is when they're separated, okay? One of the things to point out that we're going to see this chapter is this double-sided arrow. So this double-sided arrow tells us that we are in equilibrium. So in equilibrium, we're going to talk about it at length at the end of this little video, but equilibrium means that we have the forward reaction and the reverse reaction happening. So that's why we see the double-sided arrow, because it's going both ways, okay? So the concentrations of hemoglobin, oxygen, and then both of those bound together, they're all interdependent. So in this chapter, unlike what we did for kinetics, in this chapter, we're going to be looking at both the reactants and the products. So we're going to keep our eye on both sides of this reaction arrow and see how everything is interdependent or interrelated. Okay. The relative amounts in equilibrium are related to something called an equilibrium constant, K. So we are going to get to know K better than you probably want to know K in this chapter. I'm just going to introduce it qualitatively, and then in the very next video that I record, we're going to start looking at what K is and how we can determine it. Okay, but for now, that interdependence or interrelationship is held up in this equilibrium constant K. Okay. So when, for this reaction, let's talk a little bit more about this idea of a dynamic equilibrium. So when we are in a dynamic equilibrium, we've got this forward reaction, we've got this reverse reaction. What's nice about this reversible reaction is that this gives us the opportunity for either to happen. So if we are somewhere where we're in an oxygen-rich environment, like let's say our lungs, we can affect this equilibrium and tell our body, hey, we're in an oxygen-rich situation. Why don't you go ahead and bind as much oxygen as you can possibly bind? And then when we get to an oxygen poor situation, like, in our muscles or while we're working out, our body says, hey, we could probably use some oxygen here. There's not very much. And it pushes back the other way to release that oxygen and give it to our muscles. So this idea of a dynamic equilibrium is how we transfer oxygen around the body. So more about this equilibrium constant K. So the equilibrium constant K is going to tell us how far the reaction goes. So does the reaction lie more towards the products? Does it lie more towards the reactants? How far does it go? If the equilibrium constant K is large, so greater than 1, pretty big number, when we mix these two molecules together, we'll see that most of them become the product. So this goes almost all the way to completion, but not 100% to completion. So equilibrium constant K is large. We know the products are favored, and it goes almost all the way to the product side. If the equilibrium constant K is small, then we stay more on the reactant side. So we mix these two molecules together. Maybe a little bit goes over to the products, but the majority of it stays as just the reactants. So small equilibrium constant, near all the reactants stay reactants, just a little bit goes to completion, okay? In the next video, we'll talk about what's big and what's small. Okay. All right, so let's explore this idea of a dynamic equilibrium. So equilibrium is when we have the rate of the forward reaction equals the rate of the reverse reaction. So this reaction is proceeding in two different directions. Some of it's going forward, some of it's going backwards, but the rate is the same. So at any given moment, our concentrations are constant, but it doesn't necessarily mean that each particle is staying put, staying constant. If one particle becomes a product, at the very same time, another particle is becoming reactants. So the rates are equal. So let's take a look at how this graph explains the same thing that I was just talking about. So on the bottom here, we've got time. So going from left to right, time is proceeding, time is moving forward. From the bottom to the top, we've got our concentration is increasing. So something down here at the bottom is low in concentration, something up here is high in concentration. So at our initial time, we've got all reactants and no products. So this is when we've got our two reactants in separate beakers. We haven't mixed them yet. So lots of reactants and absolutely no products yet because we haven't mixed them. Then we pick up our beakers, we pour them together, and so we see that those reactants, of course, are going to go down. So some of the reactants start reacting together, they're consumed, and they become the products. And of course, the concentration of products is going to go up because we didn't have any, and now we're forming some. So right here, we are not at equilibrium. Right here, our reaction is starting to take place. Then at some moment in time, we'll see that these rates start to level off. So we'll see the product concentration rises and then it flatlines. And we'll see the reactant concentration decreases and then it flatlines. These flat lines tell me that I am at equilibrium. So the concentrations remain constant over a given amount of time. Okay. Here's another look at a graph, just looking at different variables. So again, on the bottom, we've got time. So left to right, time is ticking forward. And here we see the rate of the reaction. So down here is low or slow. Up here is high, is fast. So again, at time equals 0, the rate of the forward reaction is going to be fast because we've got our two reactants separated, and the moment that we start to mix them, of course, it's going to push from reactants to products. It's the only way that it can push, okay? And at that moment where we first mix them, there's no product at the moment, so the reverse reaction is not going to happen, and then it's going to start to happen really slowly. It won't reverse until we've got enough of this product to push back, okay? So time equals 0, mix them together, forward reaction starts to happen very fast and then slow down. Reverse reaction starts slow and then speeds up. At some point, these two, forward reaction and reverse reaction, will merge, and we'll see that they will also flatline. So the rate of the forward and the rate of the reverse is exactly the same. Okay, so forward is happening, reverse is happening, but the rates are consistent. Okay, so what we're going to see is there's no net change. So if I take a snapshot every 5 seconds or so, the concentrations would be the same, the rates would be the same. There's going to be no change in those snapshots. Okay. So this gives us a little bit of a mathematical look in that there's graphs here at what a dynamic equilibrium is. Here is kind of the word definition of dynamic equilibrium. So dynamic equilibrium is a condition where the rate of the forward and the rate of the reverse are equal. When the reaction reaches equilibrium, the concentration of all the chemicals is constant. Doesn't necessarily mean it's the same. It just means that once it finds that equilibrium, that concentration is going to be constant. So we could have a lot of the reactant, a little bit of product, and that remains constant. Or we could have a little bit of reactant and a lot of beta product, and that remains constant. Or we could have equal amounts of each, and it remains constant. But we know we've reached equilibrium when we have that flat line, when we have that consistency. Okay. Just a little bit more about dynamic equilibrium. As the concentration of product increases, the concentration of reactants decrease. So that's going to be kind of initially. So the forward reaction decreases, the reverse reaction increases. That was the second graph that we saw. Once dynamic equilibrium is reached, forward reaction equals the rate of the reverse reaction. Okay, so concentration of reactants and products, again, no longer change. So just some things that we want to point out, some common areas of misconception. So equilibrium does not mean equal amounts of everything. So rates of forward and reverse are equal, not necessarily concentrations are equal. Some reactions reach equilibrium only after almost all of the reactant molecules are consumed. So in this point, we would mix our reactants together. A lot of them would react and become the product. And at that point, we would say that the equilibrium favors the product. So once it reaches that constant flat line, what we see is there's a really high concentration of products. Other reactions reach equilibrium when only a small amount of the reactants are consumed. So we mix them together. A few of them react and become product, and then it flatlines. In this case, we would say that the equilibrium is reactant favored. So a little bit becomes product, but the majority of the concentration are still reactants. They didn't react at all. Okay. So when I say product favored or reactant favored, that just tells you where the equilibrium lies or where the greater concentration is. Okay. So one of the things that we are going to talk about at the very end of the chapter, I just like to put this in the introduction so you can kind of see where we're going, see the why behind this. One of the things we'll talk about at the end of the chapter is how we can manipulate these equilibriums. So we can push it towards the reactant or we can push it towards the product side if we want to. So the body actually does a great job of this. The body's really, really good at manipulating this hemoglobin-oxygen equilibrium. For example, in the lungs, the concentration of oxygen is really high. So the body senses that there's a high concentration of oxygen, and it was at equilibrium, and it senses that high concentration of oxygen, and it says, you know what? While I have this opportunity where there's lots and lots of oxygen present, why don't I shift my equilibrium? Why don't I push over to the product side and let me bind up some more oxygen? So the hemoglobin and the oxygen combine to make more of our product. So that does throw off the equilibrium. It shifts it to the right. But then when that same hemoglobin molecule finds its way to our muscles, the concentration of O2 is very low. So it says, you know what? I don't see very much oxygen around. I bet my muscles probably are going to want some oxygen. So why don't I release this oxygen? Why don't I shift back to the left so the hemoglobin breaks down and it frees that oxygen for the muscles to use? Okay. Again, equilibrium is disrupted, but that's a useful disruption for us. This is how we get our oxygen from lungs to muscles. So this is just a quick introduction to what a dynamic equilibrium is, and then a quick introduction to the things we're going to talk about at the end of the chapter. So how can we shift that equilibrium? I hope you guys found this helpful.